Okay, so section 4.1 is exponential functions. I do not have a schedule or a packet for you. I will get it for you on Monday and I'll post it on D2L. Okay, so we are starting a whole new set of functions at this point. So we've gone over like linear functions, we've gone over quadratic functions, we've gone over polynomial functions, we've gone over rational functions. This section is covering exponential and logarithmic functions. And then that is all the functions that we're going to cover in this class. Exponential functions are specifically, we've had, like we just finished polynomial functions that have exponents, like an exponent of 2 or an exponent of 3 or 4. So they had a degree of a number, right? In this case, exponential functions are functions that your exponent is where your variable is at. Okay, so your function looks like this: f of x equals some base b to the x power. Or you could also think about it as y equals b to the x power. And b is a positive number other than 1. It can be a fraction, it can be a whole number, it can be a fraction that's bigger than a whole number, but it has to be positive and it's some number other than 1. And if you kind of think about it, if it was 1 to any power is just 1. So that's just like a constant function anyways. Okay, so let's do a problem like just an evaluating problem. So if I gave you the word problem and I said that f of x equals 4.2 times 1.56 to the x power. We said that function models the average amount that you spend shopping after X hours. And our question is, what is the average amount after 4 hours? Okay, so in this case, this tells us that x equals 4, and we want to plug it into our function to figure out how much money you spent if you shop for 4 hours. So we're going to find f of 4 equals 4.2 times 1.56 to the 4th power. And you can just type that directly in your calculator. If you needed to do it piece by piece, the first piece you would do is the 1.56 to the 4th power first, and then you would multiply that by 4.2. But you get 24 point, I did something wrong. Did I do something wrong? Did I write it down wrong? Oh, there's the problem. I wrote the problem down wrong. It's 42.2. Sorry about that. And so 42.2, so it's felt like $24 is not very much money to spend shopping after 4 hours. 42.2 times 1.56 to the 4th power. That's better. $249.93. Okay, so the next thing we want to talk about is this base. This base, depending on what number it is, it kind of affects your graph differently. Okay, so we could have a graph that is exponential growth or exponential decay, and that depends on what the base is. Okay, so exponential growth or decay. Okay, so exponential growth versus exponential decay. Growth is something that's getting bigger or increasing. Decay is something that's getting smaller or is decreasing. Some real life examples of each of these things that grow exponentially, hopefully your money in an account, right? Like a savings account or an investment account. Hopefully that is growing exponentially and is getting bigger and bigger and the amount of money you have is increasing. Other things that grow, unfortunately, are also like loans. If you take out a loan and you're not paying it off, it's going to increase in the amount of money you owe because you're getting charged interest for it. What else grows exponentially? We are in a pandemic right now, and that is something else that grows exponentially is like a sickness or bacteria or things like that. Exponential decay. Oh, and I feel like maybe I'll research this weekend and bring a problem, but that was the whole idea of remember back in March and April when it was like slow the curve, like that's the whole idea here was things were going to grow so fast exponentially that we weren't going to be able to handle all the people in the hospitals and ventilators and all that kind of thing. So the idea was to social distance so that it did not grow as fast so that we could handle the amount of people getting sick. Okay, so real life, very applicable at this moment in time. Exponential decay, things that decay are everything. Unfortunately, like when you buy a car, that decreases in value like the second you drive it off the lot, but then also as you drive it every single day, it decreases in value. Other things that decay, like minerals, science, carbon dating, all that's based on exponential decay. Okay, so there's some ideas of exponential and growth and decay. The way that you can tell if something is exponential growth or decay just from the function is growth is a b value greater than 1. So your base is a number greater than 1. Decay is a number, remember this can't be a negative number, so it has to be a number in between 0 and 1. Okay, so in between 0 and 1. Okay, so the idea of something being a decimal or a fraction could be a growth or decay. It just depends on what that fraction is. Okay, so if that fraction was 3/2, that's still exponential growth because that's a number bigger than 1. But if it was 2/3, that would be decay because that's a number in between 0 and 1. Okay, so we have what is called, so like this number B could be any number. It could be 5, it can't be 1, obviously, and it can't be a negative number, but it can be any number other than that. It could be 5, it could be 100, it could be whatever. We have something called the natural base. Okay, the natural base, and it is represented by the letter E. E is Euler's constant. It's EULERS or apostrophe S. Okay, and E is just a number. It's a big long decimal. It's an irrational number. It's kind of like pi. Okay, so it's essentially pi, but it's a different context for it. E is the number. If you type it on your calculator, I'll show you how to do that in a second. It's 2.71828, and it goes on forever and never ends, never repeats. Okay, it's an irrational number. This constant is used a lot in nature. It's also used a lot in like calculus and physics. So if you're going to be spending any amount of time in a science field or a math field, you will get very familiar with this constant. Oh, I just wrote on myself. Dang it. Okay, it is called the natural base. So lots of times we will see this function written as f of x equals e to the x power. That e is not a variable, it is a number. Okay, so just think of e as a number, and it's a number 2.7 if you wanted to approximate it. Okay, so that number, the way you typed it on your calculator, if you look over here by the number 4, you see ln, and above it you see e to the x power. We usually raise e to some kind of power. So if you just wanted to type in plain old e into your function, you would type in e. It's going to try to raise it to a power. What power would we raise it to if we just want regular old e? E to the first power. Okay, so if you want just the right number e on your calculator, you have to do e to the first power, and there's the decimal for it. In most cases, you're raising e to some power other than 1, so that's the reason why it's automatically like that in your calculator. Okay, so this e to the x power, this is called the natural exponential function. Very interesting though. The number e, like the Euler's constant, is used in functions like whenever, if you look at plants, you could like look, there's tons of videos on YouTube about this, but if you look at plants, like the way that the leaves grow, like as a plant grows, the number of leaves is like based on this constant. Also, population growth is big time based on this constant. Like usually if you have a function for population, you're going to have e in it. Okay, so let's do a word problem like that with the population. Okay, so here's our word problem for that one. F of x equals 1.26 times e to the 0.247x. This function models the gray wolf population. And f of x is the population, and it's x years after 1978. So we want to determine the population, let's say this year, in 2020. Okay, so the number x that we're plugging in is the number of years after 1978, right? So 1978 would be like year 0, 1979 would be year 1, 1980 would be year 2, so on and so forth. So what year would 2020 be? How would you figure that out? Subtract 2020 minus 1978 gives us 42. Is that right? Okay, so we're going to plug in the number 42. So f of 42 is 1.26 times e to the 0.247 times 42. Practice putting that in on your calculator. So 1.26 times e, put in the second ln. So e to the 0.247 times 42. Let me delete. And I got 40. I feel like that's wrong too. 40. Huh? Oh, 40,340. I'm just not doing well today. Okay, so we got in year 2020, the population is 40,340. It's 40.5. If we're talking about gray wolf population, we wouldn't put a decimal here. You could argue to round that up or down. Like, I think you could argue it either way. So you could either say 340 or 40,341. Either one of those work. Okay. Questions about that? Okay, the most important part of this section, I feel like, is the money part, the compound interest stuff. So let's talk about compound interest. We have two formulas for compound interest. The first formula for compound interest is, this is things that are compounded in times per year. And let me talk about what that means. Okay, so if you put money in an account, like at the bank, like a savings account, or if you put it in an investment account, or even if you borrow money, like take out a loan or take out a mortgage or something like that, interest is accrued on that account. If you are putting money in the bank or investing money somewhere, you are earning interest off the money you're investing. If you're taking out a loan or doing a mortgage, you're paying interest on the money that you're borrowing, right? So interest could be good or bad, basically depending on if you are the one earning the interest or you're the one paying the interest, okay? So interest is accrued on pretty much everything, every amount of money right now. And the way that interest is like determine what you're paying in interest is based on when it's compounded, okay? So for example, let's take a savings account. Your savings account, say you put $100 in your account, and let's pretend like it has a 5% interest rate. It doesn't, it has like a 0.05, but regardless, 5% is an easy number. Okay, so month one, your $100 that you put in your account. On month one, you have $100. At the end of the month, the bank will figure out how much interest you earn on that account. It'd be it'd be $5 you earn, so they deposit that in your account, $105. Okay, month two, you now have $105 in your account. You calculate the interest at the end of that month. 5% of 105 is more than $5. Is $5.25. This time you get $5.25 added into your account, so you have $110.25. And then the next month, same thing. You multiply that times 0.05, add it in. This time it's $5.51. So you're $110.25. When you add 551, you now have $115.76, right? So do you see how it's not the same amount added in every single month? Same thing when you're paying on a loan or paying on a mortgage. If you have paid it down some, you're paying less interest in every month versus if you just paid like a whole lump sum. Does that make sense? Okay, so compounding is figuring out how much interest you accrued at that point. Okay, the n times per year is how often it gets compounded. Okay, so that example we just talked about, your savings account, n times per year, we said that was monthly. How many months are in a year? 12. So n would be 12 in that case. Okay, so the whole idea of n, if n was monthly, n would be 12. What about if it was quarterly? How many quarters are in a year? 4 quarters in a year. Each quarter is 3 months. So it's like every 3 months you're getting your interest accrued. What about if it was weekly? How many weeks are in a year? 52. If it was daily, how many days are in a year? 365. What else? What about if it was, I think one you have on your homework is biannually. That means 2 times per year. And I think that's all your options. Technically, you could do hourly or every minute or every second, technically. Okay, so the formula for this is A equals P times 1 plus R divided by N raised to the NT power. Let's go over what all these things mean. The A represents the final amount after you accrue your interest. The P represents the principal, Principle, not principal, like school. Okay, the principal, which is the original amount. That's what principal means. The R is a rate, and your rate's given to you as a percent, and you have to make it into a decimal. Okay, so just a reminder, your percent needs to turn into a decimal. How do I change a percent to a decimal? Move the decimal to the left 2 times, right? Decimal 2 times to the left. So for example, 5% would be 0.05, 20% would be 0.2, so on and so forth. And then we already wrote N. N is a number based on how many times it's compounded per year. And T is the time in years. So if it's in an account for 1 year, T would be 1. If it's in an account for 5 years, T would be 5. If it's in an account for 25 years, T would be 25. Okay, so let's do a couple of problems. Okay, so the first problem we're going to do is it tells you that you invested $10,000 and let's see, how much money will you have after 5 years with an interest rate of 8% if it's compounded quarterly? Okay, so I'm going to use that formula. My A value, do I know the final amount? No, that's what I'm looking for, right? P, do I know the principal, the amount you put in? $10,000. Do I know R, the rate? 8%. I need to turn 8 into a decimal. Yeah, move it over to the left 2 times, so it's 0.08. Do I know my N, the number of times compounded per year? Quarterly tells me 4, and T, the number of years, is 5. So when I put that in my formula, I get A equals P, which is $10,000, times 1 plus my rate, 0.08, divided by N, which is 4, raised to the 4 times 5 power. If you're typing this all into a graphing calculator, that is totally fine. You got to multiply this 4 times 5 first, or you have to put it in parentheses if you're putting it in your calculator. Otherwise, it'll raise it to the 4th power and then multiply it by 5. Okay, so you could just type it all in all at once. Times 1 plus 0.08 divided by 4 raised to the 4 times 5 is 20. And you get $14,859.47. You will always round to the nearest hundredth here because we're talking dollars and cents. If you did not have a graphing calculator, especially like if you're doing this on your phone, they aren't fun, but you can do it. Let me show you how to do it. To do it on your phone, you have to turn your phone sideways. And you have to do what's inside the parentheses first. So you start off by dividing 0.08 divided by 4. You get a decimal. You need to add 1 to that decimal. So add 1 to it. The next thing you do is you raise it to the power before you multiply, because exponent rule, not exponent rules. Order of operation, we do what's in parentheses first, and then we do exponents, and then we do multiplication. So you have to do that exponent first. If you don't do that exponent first, if you multiply by 10,000 and then raise it to that exponent, you get a ginormous, huge number that is not reasonable, unfortunately. So to raise this to a power, if you look over here, my powers, I have x squared, I have x to the 3rd, and then it says x to the y. That's the one I want to use. So I'm going to click on that. So I can raise this to a power now. Just heads up, if you have Android, I think it's y to the x, it's the same thing. But I want to raise it to a power. The power I want to raise it to is 20. So I type in my power and then I press equals. And that's my number, that decimal raised to that power. And then now you multiply this by 10,000 and you get your decimal of $14,859.47. Okay, so inside out, inside parentheses, exponent, and then multiply by the number. If you get a number that it says E, like let me show you, if you raised it to the power, when it, I don't even remember what it was, 1.02. If I multiply that by 10,000 first, and then try to raise it to the 20th power, it's E to the 80. Like this says there are 80 digits in this number, like a huge number. Okay, so obviously that is not correct. Okay, so that is your answer for if you took that money at that interest rate and compounded it quarterly. We have another formula. This is the one you use if it is compounded a specific number of times per year. We have another formula called, it's for when you compound something continuously. So it's like compounding every second of every day. That formula is A equals PE to the RT. P or A is still your final amount. P is still your principal or your original amount. E, what is E? Yeah, it's a number, Euler's number, right? 2.71828, blah, 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 blah. So E is just a number that you're putting in your calculator. What's R? The rate, again, turn your percent into a decimal. And T is your time in years. Let's do that exact same equation as before, or same situation as before. So we're still going to do $10,000. We're still going to do it for 5 years. It's still going to be an 8% interest rate, but this time, let's say it's compounded continuously. Let's see what the difference in the numbers is. Continuously. See which one's more. Which one do you think is going to be more, compounded continuously or quarterly? It seems like it should be continuously. Which if you're the one earning the money, that's awesome. If you're the one paying the money, that sucks, right? Okay, so when I plug it in this formula, A equals P. P is 10,000 times E to the R. What's my R value? 0.08, right? Remember, you got to do the 8 as a percent, move it over to the left 2 times, and you get 0.08. To the t is 5. Put that in your calculator now. 10,000 times e to the 0.08 times 5. I got $14,918.25. Okay, which one is more money? The continuously. It's not by much. It's like $70, right? 918 minus 859. Oh, no, $59, almost $60. But I mean, $60, 60 bucks. I'd take 60 bucks right now, right? So that's how you use each formula. The way you can tell which formula you need to use, it will tell you compounded. That word will be in all the problems, and then it will either say continuously or tell you something else: weekly, daily, monthly, quarterly, biannually, so on and so forth. If it says continuously, you use this formula. If it doesn't say continuously, you use the other formula. Questions about that? Okay, we're gonna stop there. And that's pretty much all your homework. Next time we will get into logarithmic functions. We are going to talk about the graphs of exponential functions a little bit more next time. And y'all have a good weekend. I'll see you on Monday. I'm gonna stop recording real fast. Just a second.